Welcome back to Pacing Equilibrium in First Price Auction Markets. This is part 5. And in this video, we are going to take a look into the code, which is based on the algorithm described at the end of the previous video. And using this code, we will be able to actually compute equilibrium prices and allocations for some examples. So to implement this algorithm, we actually need two functions. One of the function is this demand query function, that given the prices of the items, bidder should be able to compute its demand and report it back. This function is really simple. So given the prices, the bidder would consider the items in the descending order of the ratio of value to the price, and it would go over the items in this order and spend his budget on the items. If this the ratio for this item is better than the minimum ROAS, the constraint on the ROAS for this bidder, given that there is no overselling constraint, so the bidder could demand as much of this item as he wants, this cycle actually never steps to the second item. It just either chooses to spend all of its budget on the best item, or it could happen that even the first item is not good enough, so it violates the constraint, and in this case, there will be zero demand for this item. Okay, and now the main function, the main iteration. In the main iteration, we start with some initial prices. Also, we either get the minimum ROAS constraints of the bidders, or if they're not given, then we assume that they are all ones. And then in every iteration, we declare the prices, we broadcast them to the bidders, we execute those demand queries on the side of the bidders, and get the bidder demands back. Then we compute the update for the prices according to this multiplication formula, and also we track the current average, this weighted average, as if we would return the result at this point. So this is according to the formulas given in the end of the previous video. So having this, we can now consider an example. So in this example, there are two bidders and two items. The bidders have budgets of 5 and 2. And this is the matrix of the VIJs, the values. So the first row is the values for the first bidder, and the second row is the values for the second bidder. And note that even though the second bidder has smaller budget, it also happens to have larger values, and this is something that will allow this bidder to win more in this auction. So let's see how it goes. This is the initial prices, and eventually prices converge. The price of the first item is 2. And the second item, the price for the second item is 1 1/3. In this case, bidder number 1 chooses to demand about 2/3 of the item number 1 and 0 of the item number 2, and all that remains of these items goes to bidder 2. So we can see here that when we are converged to the equilibrium, we get this market clearing conditions approximately, that all the items are sold completely. Also, we can see that bidder number 2 spends all of his budget. This is the ad spend. Bidder number 2 spends all of his budget. So this means that he could get ROAS that is better than the constraint. On the other hand, for bidder number 1, he does not spend all of his budget. His budget is 5. He only spends 1.30 something. And this could only be possible if he actually hits the ROAS constraint. So this explains why a bidder with less budget could actually buy more in this auction. This is because of the ROAS constraint, because of values. The values for the second bidder are better, so he can move forward, he can raise the prices and get the items at the prices that are almost not acceptable for bidder number 2. I'm sorry, bidder number 1. Here's the next example, the same thing, but now we update the ROAS constraints from 1 to 2. And in this situation, everything goes to bidder number 2. So bidder number 2 just buys both of the items. Why is that? Because again, the values for bidder 1, even though he has larger budget, he cannot spend it because spending it would require to violate the ROAS constraint. So the prices goes up, the ROAS constraint prevents this bidder number 1 to buy anything at those prices. So everything goes to bidder number 2. And again, given that bidder number 2 spends all of his budget, he can have a ROAS which is better than his constraint. And for bidder number 1, the ROAS is really not really defined because he just does not buy anything. So according to the formulas from previous videos, we could also say that he gets the ROAS of 2, but this is just because he gets to multiply his budget by this ROAS constraint, because the value part of his utility is just 0. So there is an interesting question that could be asked here. So the bidder number 2 gets everything in this situation and pays all of his budget. Is it possible for him to actually manipulate this and not report his full budget? Maybe like reduce his report a little bit and still get both of the items and full value of those items, and in this way improving his ROAS. And indeed this is true. We can simulate this easily. It turns out that the bidder number 2 can actually lower his budget report to about 1.7, and in this case he would still get the full value, both of the items and the full value of those items, and he will also get a better ROAS. So he had the ROAS of about 0.4, now he has the ROAS of about 0.33, or this is going to be 1 over this number, so the ROAS of 3, and here he had the ROAS of 5/2.